So in today's video, I'm going to discuss variable gradient method as I have discussed or means pointed out the difficulties with our normal means Lyapunov function. Like one Lyapunov function advantage is that it gives us the sufficient condition. Like if you are fortunate enough to pick up a Lyapunov function, and if you fortunately observe that at your first attempt you have got a positive definite function whose time variation is negative definite, then you can draw an assumption, draw the inference that it is like asymptotically stable at origin. For your reference, I would like to mention once again that we are discussing a system that is autonomous and a system that is also means being autonomous. It becomes shift invariant, and we can apply certain manipulation that even if the system origin is not at equilibrium, we can, like equilibrium is not means located at system origin means coordinate system origin, we can do some mathematical manipulation to bring it there at the system origin. Now here what we need to see or need to check that, as it has already been pointed out, that we need to carry out several iteration, and it is just like a trial and error and game of gambling to pick up Lyapunov function. We want something definite. Now what is that definite method that is known as variable gradient method? Let us consider that we have Vx be a scalar function. Of course, it is a scalar function of x, where x is a vector field, and this gx is del v, where del v is fine. So we can write as v dot x is not explicitly dependent on time, rather we should write it here for more clarity. We can write so here you will get I just intentionally dropped this t because we are dealing with an autonomous system, and unnecessarily writing t so many times will only means complicate and make this representation cumbersome. So what we know about means gradient of a scalar number, that gradient is irrotational. Like if you obtain the curl of a gradient, you will always find that gradient will give you 0. So if you want that, means we can exploit that while selecting a suitable gradient function for gx. So if that is the case, then what we can do is that we can write that any gradient function is obliged to, like, we can compute the Jacobian matrix, this, and this Jacobian matrix must be symmetric if Gx is gradient of a vector, or else what I have said to you that for an irrotational vector field, if you take curl of gradient, it should give you 0. But so that 0 implies what? That 0 implies right. Now, this constant we will exploit several times to nullify that, or means discard the unnecessary elements, or make sure that our gradient function is work properly. Now, see what we can do here is that if it becomes this, then another conclusion we can draw: the gradient, integration of gradient will become independent of path, and therefore what we can write that Vx at a time will be but this like what I'm trying to say in two-dimensional plane, I can show you. Suppose this is your final point, this is your final x, that is x1, x2, and say here it is your initial position, this is x0. So what is your means trajectory will try? The trajectory means will means state trajectory will traverse in this way. But while evaluating this integration, as these means gradients are independent, or gradient means if it satisfy this symmetry, they will become independent of the path which we follow to reach from final to initial, initial to final. So what we can do, we can take a simple simplifying measure, like we first carry out integration in this direction of x1, and then we can carry out the integration in terms of x2, like breaking the n-dimensional integration, means from one n-dimensional point to another n-dimensional point, and calculating the gradient. What we are doing, we are breaking it into n parts, where we are evaluating only a means evaluate the integral with respect to a single variable variation. Instead of calculating the integral simultaneously for n ordinate variation, we are calculating integration for one ordinate variation, and that we can write here like So this integration path, when you take what I told you, if I have to write it in mathematics, then what we should write, like Vx will become an integration from 0 to so on. Sorry. Here we know that this first coordinate already we have reached x1, so let us keep it fixed. And then here it will be tau 2. Tau 2 will only vary in this integration. So similarly we will have g3 x1 x2 tau 3 d tau 3 plus 0 x n gn x1 x2 xn minus 1 comma tau d tau. So if you evaluate this integration, you will get the desired result. How? Let us check it. Let us check this method here with an example. Let us consider a second order system. Where h is a nonlinear function, a greater than 0 and h is locally Lipschitz. With x0 is equal to 0 and tau h tau greater than 0 for all tau not is equal to 0, when tau belongs to d, or we can consider that tau belongs to some range. Right. Now what we need to check is that obviously b and c are positive constant. So what we can see here in this representation, that this is actually, if you observe it carefully, then it is almost like that pendulum equation where this h is like minus a sine x1, and this unfortunately this a actually become b, and yeah, no need to write it in this way. It's always a is a constant multiplier. Now here this actually resembles the special form of pendulum with friction. Now we encountered that in case of pendulum, had we considered a very straightforward and naive formulation for forming our like Lyapunov function, they need to be like half x1 square plus half x2 square. But this is quite the opposite. Means in this case, what we discussed, that had we considered it, then we would have found ourselves in a difficult situation where there is very difficult to move means in any direction, because your Lyapunov Lyapunov function derivative will result in, or would have resulted in, means a sign indefinite function if you had selected it like half x1 square plus half x2 square. That is why we have selected certain other function. But now, as I discussed, that for extremely complicated system, that is quite larger than two second order system, how to accurately guess Lyapunov function, and that is why we are doing this. Now see here, what we can write is that to apply variable gradient method, what we need to check is that there are two so now del g2 del x1 is equal to del g1 del x2. So what we can write is that v dot x is equal to now here, what is our objective? Instead of is doing a random guess, here what we are doing is that we are considering uh, gx that satisfies this condition, in addition that gx satisfies this less than 0. So if we integrate it, then it will result in now here let us write the generic representation of gx. So as gx emerge by or this gx emerge as a gradient of your scalar function, so you must have the idea of gradient in your mind. Gradient generally represented by column vector. We can write alpha x x1 plus beta x x2, while this side will be gamma x1 plus delta . So if this is our case, then what we can get, that these are our goal is to find out this gx. So what we will get if we do this, like if we try to apply you will find, let me write it here because again I have reached the end of the page, like um, plus this whole thing should be is equal to, this is the problem. Whenever I try to do some serial derivation, I find myself at the end of the page. So we can write here that the other part is equal to what you can write this is our G2, so x1 delta x del x1 plus gamma x now this will be what? This is complete equation. Now from this we need to figure out the derivative. So derivative, what would be the derivative? Like v dot x you will find it will become minus alpha gamma x x1 x2 minus delta x x2 square minus delta x. Actually inside this actually we should write it more clearly, like we have no idea that whether which x, it may be so happen that alpha delta beta all of them are dependent, or at least a few of them are dependent on both x1 x2, a few may be dependent on only x1, a few may be dependent on only x2. So these kind of things are means quite natural and can happen here. Now then it is and then this is our expression of v dot x. Now once we get this v dot x, what should be our objective is to keep all the sign definite terms like having x2 square or x1 square associated with them, and try to drop all the means terms that is having some sign means change or sign indefiniteness. So the terms that we can pick up here is like alpha x, x1, x2, minus alpha gamma x, x1, x2, minus 2 8x1. However, this one seemingly means having some uh, may give you an impression that it is having cross terms or sign indefiniteness, but if you observe minutely, you will see that this is x1 and this is hx1. So if we impose certain condition on x1, it may happen that we find some region where this holds sign definiteness. However, for all these having these cross entries, it is impossible for them to exhibit any kind of sign definiteness. So let us drop them from this expression. However, not only dropping them from the equation is our objective, rather from that we want to figure out some or extract more information. Anyway, so our v dot x becomes this. Clearly these two are sign definite term, and also as per my claim, for some value of x1 or even for the entire x1 range, this is also sign definite. Now what we can do here is that doing a very simple thing, that we need to simplify things, right? So how to get them 0 or how it becomes 0, we can do what? We can assume that a few of them are constant. Like, let us consider. Now here this is actually a random guess. Like you may ask me that why not the means among these four, why only they have been chosen rather the means keeping the alpha constant. So basically what is our goal? We are looking for a very simple expression of our Vx. So for that, what we started with a b dot x, and then for b dot x we are having some means we are trying to reduce the computational burden, right? So here you can see that these all of them are like facing each other. Now what we can do further, that this alpha x, it means if we are interested to ensuring that alpha x depends only on alpha x1, then what we need to do is that we can that symmetry is required, and by symmetry I want to mean that, where is that? Yes. So by symmetry, if you want that alpha x is only dependent on x1, So obviously this term will give you 0, as well as somewhere, uh, okay, so this term will give you 0. Now you will be having, since all this we have assumed that beta, gamma and delta are constant, all of them will give 0, 0, 0. However, you will see that these two will still remain, and we will have no other choice other than saying that beta, we have to select them in such a way, those two constant, that they are equal. So you will find that what is happening here. Yeah. So what you will find here, that after doing so, we will get gx, that is having alpha gamma x1 plus delta h x1 plus gamma x2. How we can write this? Sorry, here it should be x1. So how can we write this? See here in this expression, like where was G? I have written G somewhere, but I have forgotten. Yes, this is the structure of G. So alpha x x1. Now we can write it in this way. So what we'll have here, like alpha x gamma x delta 1 plus beta x, we are getting beta x is equal to, since beta is equal to gamma, so we can write it is gamma x2. Now the second row will be gamma x1 plus delta x2. Now how to get like Vx? Vx will be what? Vx will be since we are considering a path along which entire path x to 0, so no need to consider this one, so we can make it 0. Achha. Here what we need to do is that we need to replace them by some dummy variable. Similarly, here you will have right. So after doing all this, you will find something. That is actually I am doing this step by step just to make you understand that how laborious and tenuous this job is, and actually of no use, because even for your small system, if you try to apply them, then it will also result in a kind of catastrophe. So here Just a minute. I think I have made some mistake here. Delta alpha x2 comma x. Yeah, this will not be alpha. This is actually A. A, please correct it. It is A. So if that is A, then you will have accordingly you need to change little, like A gamma tau. So here you will have A gamma x1 square plus like delta from here also you get a delta your x1 naught h tau d tau plus you will have gamma x1 x2 plus half delta x2 square. Now you can have a structure like this from this one. Don't get worried with this existence of this cross product. We can have a structure like A gamma, and here it is delta, then here it will be gamma gamma. So how we can have this gamma gamma in these two places, like if we choose that delta greater than 0 and like with this actually we are trying to represent this above equation in this form, half x transpose px plus so here again if you do further simplification, you will get some value of Vx that will be, I'm not doing the intermediate steps because it already becoming very tiresome and unnecessarily we are spending effort, because this method is itself is of little use. But the purpose of showing you this is to make you understand that we should not waste our energy in everywhere or in every possible way. Rather, we should use it in a judiciously and with a definite objective in our mind. So this is, if you consider this is at origin, it is 0, because at origin your the first part and also the second part, this one also boils down to a point, and therefore it will also become 0, because point under any point your area under the curve enclosed by a point is 0. Now, whatever be the case, it is 0 at origin and otherwise it is positive definite. We understand that. Now, this is true for the domain. And also we can see that the origin is asymptotically stable, because we have started with the fact that v dot x is negative definite, right? So that's all. Now we'll discuss some different issues Now we'll discuss something that is very interesting. It's known as region of like domain of attraction or region of attraction. Actually, what it is, whenever you get to know that your system is what to say, that it's a asymptotically stable system, then obviously one question that will knock you is that how far from your equilibrium point, although you have considered equilibrium point at 0, then how far, if in terms of norm or something, you can move away from the equilibrium point and still find that if your equilibrium is initial point falls within that zone, your state trajectory experiences a drag or a pull towards your equilibrium point and thereby satisfy the characteristics or resemble the characteristics, not satisfy, rather resemble the characteristics of an asymptotic stable system. So this is very interesting to understand that here we need actually quite often one thing, it's very obvious that if a system is stable everywhere, then it's very good, and this is something we know or we define as like globally asymptotically stable system. So what is an example of globally asymptotically stable system? I can give you a few examples of linear and non-linear system. They are globally asymptotically stable. Here x belongs to R. These are globally asymptotically stable system. Like anywhere other than origin, it always experiences a drag, and whether you move away one light year from your origin in your state space, still the initial condition, the initial state variable will experience a drag towards your, for this system will experience a drag towards your system origin, and it will be drawn towards your system origin with time. So this is very important feature of global asymptotic stability. However, if I ask you to consider this kind of, these are global. Having the entire however, if we consider a system like so, for all this system having even power of x or means having a sign definiteness for x, you will see that they are stable when x is in this region, whenever x belongs to then these systems behave like a stable system. Like if you take the positive side of the real number line, these systems behave like a stable system. Even if you move very far away from the origin, still it will experience a very high attraction towards the origin, and thereby resembling the characteristics of a stable system. However, for these systems, all these systems, if you are means in this region, like if you consider air means then you will see that these systems are totally exhibiting a tendency to move away from that origin. So this type of system, we can say it's a semi-stable equilibrium. However, for these kind of systems also, it's very clear to figure out that what is going to happen. But means for some other system, there exists a few other systems where we will be observing that it is like, let me give you one example. So what you can see here, that unlike the previous case, now you can see that this will be like, if this is your real number line, let us consider extended real number line with infinity included. So here you can see that as long as you are at A, means in this region it will experience stability. Then here, or let me just make it like this. So in this region, that x minus a, here you can see that as long as this x is like okay, now it's better. Now as long as this x is less than a, x is less than a, then this region gives you a stable operation. But once x become greater than a, like if unfortunately if you started taking any x naught that is located means a distance that is greater than a, then in this region this system is unstable, right? However, from 0 to a it's stable, and this side also you will see that this side it is totally unstable for the entire operation. If you consider a is a positive number, then for entire operation it is unstable. So what we can see that now the system is only locally stable, locally asymptotically stable, and that is confined within this region. So this is actually, since this is a very simple expression of linear system, we can we can figure it out very quickly, very easily, that what could be the case here. But if we have something like that, the growth, or sorry, the system state space is so complicated, then we will not be able to, just by observation or by inspection, we will not be able to figure out that the region of convergence or region of attractions, not convergence, region of attraction for a given system. Now for that region of, in order to estimate region of attraction, we will try to devise some tool so that by exploiting those tools we can get an anticipation. Quite often what happens, that this anticipation what we get from application of those tools, they gives a very conservative estimate. Like in reality, you will see that your region of attraction is much bigger than what you have as estimated using those algorithms. But that is a blessing in disguise, because there is no harm. Like suppose there is no nothing wrong if you know that 70 is the pass marks and you prepare yourself for that, and later on after examination is over you know that 30 is the actual pass marks, but since you prepare yourself for 70, you will be in a, means you will get an edge in this condition. So this is very important here. So that's all. Now here we would like to discuss another few things. Oh, this this is 50 minute. I just so one more thing that very obvious that we will discuss in our next. I was about to discuss it in this lecture, but then it will become a bit problematic. So I would like to schedule it that we will figure out what is to be done to two things we will study in our next lecture. One is when we can claim a system is globally asymptotically stable, and when we will be able to see that a system is like uh, what is the estimate of the region of attraction or region domain of attraction. And then in that lecture or probably in the next lecture we will discuss invariance principle. So with this I would like to conclude because here I don't have enough time to continue and discuss, although that this theorem is a small one, but with proof it will take another 15-20 minutes, so better to conclude here. There is some problem, it is not a means I'm not able to click, don't know what is the case. Strange. Actually, we are done for this lecture, but due to some computer problem, I cannot close it right now. Not sure what is wrong with this